In this video I'm going to be talking about stability. Now stability for single step methods all comes down to the idea of that step length h. Now if h is too large you can have an unstable method and it's of no use to anyone. So what we tend to do is we derive or determine what's called a stability function. Now the stability of ODE solver methods can be examined by using this linear test equation. So we always base our stability analysis on this. So we have a linear ODE, so we have y dash equals some coefficient lambda times our function y. And lambda could be any complex number. So we rewrite the ODE solver using this. So our next step solution, yn plus 1, is equal to some function rz multiplied by our current solution yn. Now rz is known as a stability function, and z is our step length multiplied by that lambda coefficient. So for each method, each single step method has a individual stability function, and we use the stability function to analyze the stability properties. For single step methods, the stability function can be represented by this equation here. So we have r equals some function of z, p, divided by some function of z, q, and p and q are both polynomial functions. So if we have a look at an example, so we're going to use the Euler method to solve our test equation y dash equals lambda y. Okay, so you should be familiar with the Euler method by now. So it's our current solution plus step length h multiplied by whatever our ODE function is. Now for our test equation, our ODE function is lambda y. So instead of fty, I've got lambda y. And recall that z, if I go back a slide, recall that z is equal to h times lambda. So what we can do is I can rewrite this as yn plus z times yn, which if we factorize we have 1 plus z as a common factor, and that's multiplied by yn. Now if I go back a slide again, the definition of our stability function was some function of z multiplied by yn. So if we can see here we have some function of z which is 1 plus z multiplied by yn. So this is the stability function of our Euler method. So here we have pz is 1 plus z and qz is just 1. So if we were to divide this by 1, we get qz equals 1. If we do similar for the implicit Euler method, we have a different stability function. We have rz equals 1 over 1 minus z. So you can see here we have a stability function where qz is 1 minus z and pz is 1. So we can examine the stability of a method by looking at what's called the region of absolute stability. Now in its basic form, stability means we do not want our local truncation errors to get bigger or to accumulate as we step through the solution. So our errors always need to be bounded. So this leads to this constraint here. So we want the modulus of our stability function to always be less than 1. If that's the case, that means our methods will remain stable. So the values of h lambda for which this condition is met is known as the region of absolute stability, and here we have it formally defined. So it's any number z in the complex plane for which our stability function, or the modulus of our stability function, is less than 1. So the region where this is the case gives us a stable region. So it means we can determine what values of h for a particular method are stable. And we could easily represent this using a contour plot. Okay, so on the next slide, here we have a contour plot of the region of absolute stability for the Euler method. And what I've done here is I've shaded in all of the values of z for which the rz, or the modulus of rz, is less than 1 for the Euler method. So any z within this shaded region will give us a stable solution for our test equation. And I've also done the same for the implicit Euler method. So as you can see here, the shaded region, which is outside of this this oval here, the shaded region, this is all stable regions. So if we'd chosen a value of z within this region, we wouldn't have a stable solution. But if we choose a value of z in the shaded region, we would have a stable region, a stable solution. Okay, well that was just for a single ODE. What about when we have a linear system of ODEs? Okay, so we're going to look at our analysis for a system, and here we have a vector y, which is a number of y1, y2, y3, etc. And we have a coefficient matrix A, and A we're going to say is the diagonalizable constant n by n matrix. So we have n equations in our system, so our matrix A would be a square n by n matrix. And these have eigenvectors Ri, and the definition of an eigenvector means A times, or the matrix A times the eigenvectors Ri is equal to some eigenvalue lambda I times the eigenvector Ri. So this is the straightforward textbook definition of an eigenvector and eigenvalue. So if we let R be a matrix which is formed by having each column of R is the eigenvectors of A, and D is a diagonal matrix of eigenvalues, like so, we can rewrite A using a linear transformation. Okay, so our vector of, or diagonal vector of eigenvalues D is equal to the inverse of R times our matrix A times R. Now this is a linear transformation, and that's important because we can apply a linear transformation to our original system. So if we introduce a transformation where the vector u is equal to the inverse R multiplied by y, what we have is we have the linearized system. So here's our original system, y dash equals ay, or we can linearize that and we have an equivalent system which is u dash equals du. Now remember D, if I go back a slide, is simply a matrix, a diagonal matrix of eigenvalues. So what we have here, we have n equations of this form. So we have ui dash equals lambda times ui. So this lambda is an individual eigenvalue of the matrix A. So if we apply the Euler method to solve this, or to solve our original system of linear ODEs, we have this, and using this transformation we have the equivalent Euler method for solving our diagonalized system. So remember, instead of A, so it's very similar, instead of A we have D. Now D is a diagonal matrix of eigenvalues. So we have n independent applications of the Euler method which solves n linear ODEs. Okay, so let's just summarize that. So what we do when we presented with a linear system of ODEs, we examine the stability of the solution of a system of ODEs by applying a linear transformation to linearize the system. Now this linearized system is different from the original system, so if we were to linearize it and solve it, we'd have a different solution. However, the stability properties will be the same, so if we're doing a stability analysis, it is the same as the original system. Each equation in our system will have different stability properties. So one of them might be stable for large values of h, where others might be stable for only small values of h. And what we do is we use the most stringent one. So any step length h has to be stable for all equations in the system. Let's have a quick example of linearizing a system. So here I've got a second order equation for the motion of a pendulum. So we have some theta, which is an angle of a pendulum. So we have the second derivative of that, plus some coefficient times theta, plus another coefficient b times the first derivative of theta. Okay, well we have a second order equation here, so using our standard method we can rewrite that as a system with two first order ODEs. And so this gives us the coefficient matrix. So coefficient of theta 1 in the first equation is 0, and coefficient of theta 2 in the first equation is 1. And the coefficient of theta 1 in the second equation is minus a, and the coefficient of theta 2 in the second equation is minus b. So this gives us our coefficient matrix. So if we take the eigenvalues of our coefficient matrix, so if we subtract lambda times the identity matrix, and what we're doing is we're looking for the values of lambda which satisfy this equation where the determinant is equal to 0, gives us a quadratic, and we can calculate the eigenvalues as the roots of this quadratic. So now, if we were to choose an ODE solver for this problem, depending on what A and B are, or depending upon the choice of ODE solver and the step length. So for certain values of B and lambda, the Euler method may be unstable, whereas the implicit Euler would be fine. So what about nonlinear systems of ODEs? So this is with nonlinear systems, the problem is our eigenvalues will change as t changes. So what we have to do here is we have to rewrite them or approximate the nonlinear system using a linear system. Okay, so again we have this nonlinear system of ODE, so y dash equals f of y. Okay, so we have it written in vector form. Now if we let y bar be an equilibrium point, so the definition of an equilibrium point is where the f of y bar is equal to 0. So in other words, there's no change in the system at that point. And so as t changes, at that point y bar, there's no change. So we can use the first order multivariate Taylor series expansion. So for these two equations in this example, this is the first order Taylor series expansion. And since y bar is an equilibrium point, f1 y bar and f2 y bar must be equal to 0 by definition. So if I go back one, so this is 0 here, and this is also 0. And what we're going to do is we're going to let u1 and u2 be the difference between y1 and the equilibrium point y bar 1, and same for u2. Okay, so what we mean there is we can replace this bracket with u1, and we can replace that bracket with u2. So this means we have this system. So this system has this coefficient matrix. So you can see we have a coefficient matrix of partial derivatives of our functions f1 and f2. Now this coefficient matrix is known as the Jacobian matrix. So you can see the first line of this matrix is the partial derivatives of the function f1 with respect to y1 and y2, and the second line is the partial derivatives of f2 with respect to y1 and y2. So for a nonlinear system of ODEs, we can't find the eigenvalues of the coefficient matrix, as these will change as t changes. So we need to be stable for all values of t. So what we do is we approximate the nonlinear system using a linear system at the equilibrium points. And then we calculate the eigenvalues of the Jacobian matrix at the equilibrium points and base our stability analysis on those.